So let me welcome all of you for the last lecture in the series of lectures on photoelectric effect. We have spent a fair amount of time discussing the evidence for the wave nature of the electromagnetic waves through interference, diffraction, loss of reflection, loss of refraction, etc., etc. And we also pointed out how the great experiments of Leonard and Millikan, of course, the first experiment was performed by Hertz, they cannot be reconciled with the concept of wave nature for electromagnetic waves or light. So we are at an impasse. If we accept the wave nature of light, then we are not in a position to understand the results of photoelectric effect. And on the other hand, if we give up the wave explanation for the nature of light, then we would be in trouble as to how to understand the processes of interference and diffraction. So at this point, what we are going to do is to not ask how we will be able to reconcile the concept of a photon with that of the wave nature. That will be done in a much advanced course. Right now, what we shall do is to suspend our belief or whatever evidence we have for the wave nature of light and merely try to understand how in a logical manner we can give an account of the results of Millikan and Leonard. Millikan's experiments are of course the most important, and we have spent a lot of time. In other words, as I mentioned in one of my earlier lectures, we are not aiming for a complete description, but we are aiming for a simple description. Obviously, you will see that there is a contradiction with the wave nature, but as I said, that is for a future understanding at some future time. So we have to look at Einstein's explanation. We should remember that Einstein is not the originator of the concept of a photon, the so-called particle of light. This concept was actually introduced by Max Planck, and we have also discussed why Planck had to introduce that concept by looking at the phenomenon of black body radiation. Black body radiation is not a part of your course, but I was able to show you using the principle of equipartition of energy that if you accept the wave description of light, then at any temperature my energy, total energy of the wave would be infinite. That is what we found out. So there is a quadratic divergence, the picture I showed you, and Planck came up with the radical hypothesis that this can be understood. The experimental results regarding black body radiation can be understood if you imagine light to be a stream of particles. That is what he said. But Planck really did not believe in the concept of photon. He simply thought that when electromagnetic waves interact with the atoms or molecules in the cavity, because that is what you are going to look at when you study black body radiation, it pretends to be a particle. That is what Planck believed. So the great step that Einstein took when he gave his explanation was that he treated photon as representing reality in all its entirety. So he was not trying to give an effective picture. He said that light can behave like a stream of particles, and I am going to discuss that at some length. So in that sense, what Einstein did is much bolder and more courageous than what Planck did earlier. For Planck, it was a convenient language, whereas for Einstein, it was reality. And that is the reason why we have spent a long time before we write down some simple equations, because I know that all of you have solved enough number of problems in photoelectric effect. So remember the famous experiment of Leonard. This is the Millikan. This is the experiment of Millikan with sodium as the metal, the target. And you see the straight line that is coming. So this is the most surprising thing, that it behaves linearly with the frequency. The frequency is of course not entirely in the physical, in the visible region, because it is slightly above. We are looking at sodium, not at a element or a metal like cesium. But if you did that, that is what you are going to see. And this is what this is something that cannot be understood in terms of the wave theory. We have discussed it. So let us recall what are all the conclusions of the careful experiments of Millikan were. Millikan performed these experiments over a period of 10 years. It is not an experiment that was performed over a period of 6 months or 8 months or a couple of years. So there is a lot of data. The first consequence is that you need a minimum frequency for photo emission. Remember, classically, the energy of a wave is carried by its amplitude and not by its frequency. Frequency tells you how many times the wave is oscillating, whereas amplitude tells you how much energy it is carrying. They are two different things. So energy is like the intensity of the sound. Frequency is like the pitch. So I can speak at a very high pitch at a very low intensity. So there is not much energy, but I have gone to a higher pitch. Or it could be the other way around. I can speak at very, very high intensity with very loud voice at a very low pitch. Musicians can do that. They go to very, very low pitch and they can sing with a very loud voice. So that is the distinction that we have. So this is a well-established fact in all wave phenomena, including sound. But here we are saying that photo emission. So what are we saying? So let me write that down here. So I am repeating for the benefit of understanding whatever we have said so many times. So we are physicists, so we are not afraid of redundancy. So we will repeat it as many times as necessary. What we are saying is that energy required for emission of electrons. Now electrons are bound therefore, minimum energy required. Minimum energy is necessary. Without that minimum energy, I will call E minimum. If E is less than E minimum, means no emission. This is a simple consequence of the conservation of energy. You don't give enough energy, you don't get electrons at all. But what do experiments tell us? Experiments tell us that no emission takes place if nu less than nu minimum. So this nu minimum is different for different metals, and we related that to the work function of the metal. Sodium, cesium, zinc, lead, etc., etc. We looked at all these elements and it was connected to the work function through the stopping potential. I am not going to get into that. So we have saying no emission takes place if nu is less than nu minimum. So in a similar manner, no emission takes place if E less than E minimum. And since we are looking at the conservation of energy, that means that my nu is somehow related to the energy. This was the great observation of Einstein. On the other hand, Planck had already made the assumption, had postulated that for any given frequency, we can imagine energy to be coming with what? Photons of a certain definite frequency. So what did Planck say? If you have an energy density U, whatever this quantity may be, for a certain given frequency, this can be written as n into h nu. H is the Planck's constant, and this was identified to be the number density. This is identified with the number density. So what are we doing? The left hand side of the expression comes from Maxwell's theory, which tells us that light is a wave phenomenon, and we are equating that to an expression coming from particle theory, namely each photon carries an energy h nu, and there are n photons per unit volume. Therefore, the total energy density is n into h nu. So logically speaking, this is an incompatible relation. So what are we doing? We are comparing apples and oranges. The left hand side is the apple, which is coming from the wave equation. Right hand side is the orange, which is coming from the particle description. Something cannot be both a particle and a wave. It is either a particle or a wave. That is what common sense tells us. But still, Planck did this in order to understand the black body radiation. And Einstein picked up the same idea, and he said that we are going to use that in order to understand photoelectric effect. So please understand that this explanation goes against what we normally do. It requires an enormous courage and of course a lot of work at a later stage to be able to do, to be able to reconcile both the pictures. But we have to be aware of the fact that this is not a simple assumption. Now there are additional things, additional properties of my experiment. I discussed only minimum frequency required for photoemission. The next observation is that it is proportional to intensity beyond minimum frequency. Now there is no surprise about that. If I keep this sheet of paper again here, there is a minimum frequency that is required because of the work potential. Now after you cross the work potential, as you keep on increasing the intensity, you are increasing the number of photons. Therefore, if you imagine that the emission is taking place because of the number of photons, then of course your current keeps on increasing, number of electrons keeps on increasing. Therefore, this picture will be again consistent with what Einstein said. There is a linear relation that is also not surprising, because greater the energy of the incoming radiation, greater the energy of the outcoming electron. So there is a linear relation. So we have sort of been able to qualitatively appreciate that if we accept the photon picture, we will be able to account for all these experimental observations, and that is exactly what Einstein did. So the Einstein revolution, to restate, is the following thing. Radiation of a certain frequency nu is equivalent to a collection of quanta. Now the word quantum does not mean particle. Quantum means a unit. That is what is a, what is the quantum of such a thing. It comes from the word quantity. Is that okay? But we also tend to use the word particle because it is coming in discrete units. This quantum is coming in discrete units. So we are saying that radiation of frequency nu is equivalent to a collection of quanta, each of which carries an energy h nu. So this is the Einstein revolution, where he took the photon concept very, very seriously. I am going to repeat in a more quantitative way whatever I wrote there earlier. So if you look at the screen, you find two expressions. From the classical expression, you find that the energy density is nothing but epsilon naught by 2 into E naught squared. So what am I doing? I am writing E is equal to E naught cos k dot r minus omega t. My omega is nothing but 2 pi nu, my frequency. That is what I am writing. If I make use of the Maxwell's expression, the corresponding energy will be nothing but half epsilon naught E naught squared. There is something that you people have to remember here. In writing this expression, we have averaged over time. Over a period. And that is justified because even in the visible frequency, even in the visible range, the frequency is of the order of 10 to the power of 14 hertz. Every second, my light wave is oscillating 10 to the power of 14 times, and we don't have that kind of a resolution. That is what we have. Whereas the photoelectric effect, the assumption that we are making is that UPE is equal to the photon density per unit volume, that is what we are writing, into h nu. So I am writing it again so that it may settle in your mind. What we want to do is to equate these two expressions. That is what we want to do. So I use classical mechanics in order to, classical electromagnetic theory in order to get the energy density of the electromagnetic wave. Then I make use of the Planck hypothesis in order to obtain information on the photon density. How many photons are there per unit volume? And using these two seemingly contradictory concepts, what I wish to do is to understand the photoelectric effect. I have practically explained it to you in words. So all that we have to do is to do a little bit of more work and then put it on a quantitative footing. So at this point, we should remember that the Planck hypothesis was a reluctant explanation. He did not believe in the concept of photon, of limited validity, limited applicability, but what Einstein did was to take it seriously. So here is an important concept that we have to keep in mind. So what is the great difference, philosophically speaking, from the viewpoint of the way we look at nature when we say that light can be looked upon as a collection of particles? When we speak of a wave, we think of a continuous function. A wave varies continuously. A field varies continuously in space and time. That means energy at any given time is continuously distributed over all space, whatever the region is. So for example, let us consider the field produced by a point particle. Let us go step by step. So fields, classical fields. Let us look at the classical fields. Let me look at the field produced by a point particle. I say that, let us say that this has a charge q. This is at a distance r. The position vector is r in some coordinate system. I say that my electric field is simply given by q by r squared r hat. That is what I write. When I write this expression, it is understood that this r can be taken anywhere. This r can be taken anywhere. That means I can take a test charge q, place it here, 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 anywhere that you want. Wherever it is, I experience an electric field which is given by this formula. Therefore, my field is a continuous function of position. If it is a function of time, it is also a continuous function of time, and that is the reason you are able to use Gauss's law, etc., when you make use of the integration of the electric field, or when you write the potential, for instance, in terms of the electric field. What do we do if we want to get the field in terms of the potential? We take the gradient of the potential. We take the derivative of the potential. So potential is continuous. My field is a continuous function. What Maxwell's theory is telling me is that this electric field also carries an energy. So what is the other example that I can think of? The other example that I can think of is two capacitor plates. So I put a charge q here, I put a charge minus q here. So let me light a capacitor. Then in between the two plates, there is a constant electric field. And we say this capacitor stores that much electric field or that much what? Energy. Capacitor is a storage mechanism for energy, electric energy. And whenever we want, we will discharge it and the current will start flowing when I complete the circuit. That is your examples with RC circuit, LC circuit, LCR circuit, and so on and so forth, which you people will do in your network analysis or electromagnetic theory. It stores the electric field, and again the electric field in this case is given by epsilon naught by 2 E squared. That is what you are going to get. It is proportional to this. Therefore, my electric field is again a continuous function. That is, my energy density is also a continuous function. That means whenever I think of a field, I am imagining a continuum. That is the great contribution of Maxwell. That is what he said. But when I speak of a particle nature of light, I am imagining a stream of particles, and the very notion of a particle means there is discontinuity. That means there is a discontinuity and there is necessarily gap between the two particles. That is what we say. For example, when I say that my water is at a certain density or this pen is at a certain density, I know that it is a crude approximation. because if I look deep inside it using a microscope, it is discrete because there is a lot of space between different atoms. That is what we mean. So when I speak of particle nature, what are we saying? We are speaking of discontinuity in space and time. Therefore, when I say that I am going to replace a continuum description of energy or momentum carried by a certain physical phenomenon by a discrete description of the same energy or momentum, we are making a radical change. Continuity to discrete, and this is something that bothered Einstein a lot. So in one of my earlier lectures, I advised all of you to go and look up the original paper of Einstein. It is eminently readable. It is as easy to read as your 12th standard textbook. It is nicely, very well nicely written. Einstein raises this question as to how one can replace a continuum description by a discrete description, and he justifies that to two simple words in his paper, and that is what you see on your screen. He says temporal scale. That is the most important word. He uses the word temporal scale. So we should be able to understand what we mean by the word temporal scale. So let me spend some time on that. So wave nature seen over large temporal scales. This is the fundamental observation of Einstein. So as I told you, my electromagnetic wave is coming and it has a frequency of 10 to the power of 14 hertz. That is what I have. And if I perform a double slit experiment, for example, and if I put the detectors. So what is your detector? The human eye. I keep on scanning and I see maxima and minima. I know that my light does not have a response time of 10 to the power of 14 seconds. I don't have that. So what I see is a highly time averaged thing. So you can imagine, for example, a stream of particles which are coming, and let us say the changes in their positions are of the order of 10 to the power of minus 14 seconds, going up and down or whatever. Whereas the resolution of your eye or your detector is of the order of a millisecond or of the order of a fraction of a second, then there is a pretension. There is an approximation that you are going to do, that is, it is as if you have a continuous distribution of matter. That is what we are going to say, simply because of the temporal fluctuation. So whenever we are going to average over such time scales, over orders of 10 to the power of 8 or 10 to the power of 10 or 10 to the power of 12, even discrete appears to be continuous, just as everything around us appears to be continuous, although they are deep down made of molecules. By the way, when Einstein wrote this, there was no direct evidence for the molecular nature of matter. That came from his Brownian motion paper. But this is the fundamental observation that Einstein made. He said that your evidence for diffraction, interference, everything comes because you have averaged over 10 to the power of 14 oscillations or 10 to the power of 12 oscillations, whereas the emission of an electron is taking place over a much smaller time scale. In fact, I gave you an estimate and I told you it is of the order of 10 to the power of minus 9 seconds. That is what I told you. At that scale, perhaps it is not a continuum description. Perhaps the particular nature of light can be seen, and therefore Einstein goes on to propose that we need two different phenomena. Whatever takes very small intervals of time, we would need the particle nature of light, and whatever is averaged over large time scales, you can sort of approximate the discrete nature by a continuum nature. So Einstein says that it is not too unrealistic for us to assume that light is made up of a large number of particles. This is the justification. So I am going to repeat whatever I told you so that you people can read it on the screen. What Einstein did was to essentially make two simple but radical assumptions. So let me read whatever is on the screen. Two simple but radical assumptions. The first assumption is that the incident radiation of frequency nu can be looked upon as a stream of photon gas, with each photon carrying an energy h nu. I have explained it at great detail. Now that is a qualitative assumption, but in order to understand the Millikan experiment, which was done very, very carefully, we need more quantitative assumptions. And actually, I am going to spend quite some time discussing those quantitative assumptions. So let me make the assumption. Electrons in the metal escape to free space by transfer of energy from an individual photon. So I should explain that to you. So what are we saying? So you have a metal here and you have a photon stream which is coming here, and electrons are getting ejected. So this is my light, as Einstein would imagine, and these are my electrons that are coming. Now what is happening? There is a transfer of the energy from light to the electrons through photons. Now the big question that Einstein is asking himself is, how many photons are required in order to eject an electron? Are you people understanding that? That is what I am trying to say. So what is the assumption that we are making? So you have a work function phi. This has the unit of energy. So let us say it is some 3 electron volts. Now what is the experiment telling me? The experiment is telling me that nu minimum required in order to eject the electron is given by what? Phi by h. That is what is telling me. From the viewpoint of the particle nature, it is perfectly possible that 2 electrons of frequency nu minimum by 2, they could have gone, hit the electron, and the electron would have come out. So imagine there is an electron, the first photon goes and hits it, it transfers its energy. The second photon goes and hits it, it transfers some more energy. Both of them add up to this work function, whatever that energy is, and it comes out. That means it is possible that more than one electron can actually be absorbed by the, more than one photon can be actually absorbed by the electron in order to come out, but that is against the experimental result. In that case, there would have been no nu minimum. Even if the frequency was 1/3, some electrons would have been produced by the absorption of 3 photons. If it is 1/10, some electrons would have been produced by the absorption of 10 electrons. If you work out, the photon density will be 10 to the power of 12, 10 to the power of 13, 10 to the power of 14. So out of 10 to the power of 14, if some 1000 or 10,000 or even 10 million are absorbed, it really doesn't matter. In order to produce 1/10 of them, you would have been able to see electron. So what Einstein is saying is that for every electron that is coming out of the metal, there is exactly 1 photon that is absorbed. Of course, in this absorption process, Einstein is invoking a time-honored law which can never be probably violated in nature, and that is the conservation of energy. So let us go back to your screen, whatever is there. So let us look at what I have typed on my computer. The incident radiation of frequency nu can be looked upon as a stream of photon gas. Electrons get emitted by absorption of a single photon, because that is what the experiment is telling me. The third one is very, very important. Energy is strictly conserved in the process. That is very, very important for us. Maximum kinetic energy corresponds to complete absorption of photon. This is very important for us. So let me explain that to you, and that is important. Again, I have a metal and I have my radiation coming, and my electron is coming. I argued that corresponding to every single electron that is coming, I need a single photon. That is an experimental result. But now there is a converse. Is it necessary that my electron should absorb all the energy in the photon? Is it not possible that my electron absorbs only a part of the energy? How is it like? It is like collision of 2 particles. So I have a particle here, I have a particle here. So this particle comes, hits it and goes away. So in the final state, both of them are moving. Part of the energy is taken by this particle, part of the energy is taken by this particle. Such a thing is possible. But then, depending on how much energy is transferred to the particle, this fellow's particle energy becomes smaller and smaller. So I have AB, AB. As the energy of B becomes larger and larger, the final energy of A becomes smaller and smaller. So I am telling you that when B acquires maximum energy, A has lost all its energy. So that is very important, otherwise you cannot understand the stopping potential. So Mr. Einstein tells us maximum kinetic energy. So let me read that carefully again for you, which is written on my computer. Maximum kinetic energy corresponds to complete absorption of photon. Now, if you sort of look at them very, very carefully, you see there is a fundamental difference in the approach of Planck and Einstein. Planck made the assumption of photon. He explained black body radiation. What do I do with it? What do I do with that photon? But here Einstein is opening up a new world. He is saying that, oh, some photons may not give their energy completely. That means I must be able to see it experimentally. So it is opening up a new world of further experimental evidence. Is that okay? In fact, that is what I am going to do at the end. Therefore, this is significantly a better approach and an improvement over what the Planck hypothesis is. I mean, it is by no means to disrespect the Planck hypothesis, but in this context we have to understand that this was really lot of insight that was involved in it. So I simply wrote down the points because I am sure you people will solve hundreds and hundreds of problems per permuting stopping energy, stopping potential, maximum energy, incoming frequency, number of electrons ejected, number of photons in the density. So let me not get into that. So let me read it out. Suppose the work function of an electron is phi naught, then phi naught is the minimum energy required to emit an electron by irradiation. Electrons completely absorb photon for their emission, that is the maximum energy electron, and each photon carries an energy. That is what Planck is saying. So if I combine all of them, the minimum energy is nothing but phi naught by h, that is the minimum frequency. Nu greater than E naught, the current increases with intensity, I already showed you, and energy is strictly conserved in the process. So these are the points that we made, and what do we get if you plug it all? That is contained in these equations, and I am going to write them down again for you. So the incoming energy is h nu. I am going to make use of conservation of energy. What is the outgoing energy? Outgoing energy is that of an electron. So this is photon, this is the electron. So I am writing EF is equal to E electron. What am I going to write? Oh, I am sorry, that is not what I should write. I should write the total energy. The total energy of my in the final state is maximum kinetic energy plus phi naught. So what is the assumption that I am making here? The incident energy is entirely due to the photon. So let me write that. Incident energy, initial energy of the electron is 0. So when I am writing it to be 0, what do I mean by that? By that I mean that its energy is negligible. So you people can figure out what the energy of the electron is. So the initial total energy is given by h nu. The final total energy is the maximum kinetic energy of the electron because it has absorbed the photon completely. But in doing so, some work had to be done in order to liberate. Some energy had to be given, and that is your phi naught, and that is what we are writing. So we have to write these two equations, and this phi naught is what we call h nu naught, because nu naught is the minimum energy that is required. Therefore, what do we write? We combine these two equations and write h into nu minus nu naught is equal to E kinetic maximum. That is what I am writing. H into nu minus nu naught is E max because initial total energy is the total final energy, and this was nothing but the result of Millikan, because he looked at the stopping power of the electron that corresponds to the maximum energy of the photon. Therefore, now you see this very, very simple explanation is able to completely describe all the experiments performed by Leonard, Millikan and earlier by Hallowack and Hertz. So in a sense, this completes the description or the discussion of photoelectric effect, but it doesn't end there. We have to do a few more things, and let us see what we have to do. Where is the energy of the photon? That is a very, very important question that we have to ask. Where is the energy of the photon? So what are we asking? If photon is a particle, what is its mass? That is a very, very important question that we have to answer. So let me do a very naive calculation which is completely wrong. Electromagnetic radiation moves with a speed c. So what is my c? This must be 3 into 10 to the power of 8 meters per second. So that is what I have. If my photon has a mass m, what will Newton tell us? So Newton would tell us that my energy of the photon should be given by half mc squared. That is what Newton would give us, where m is the mass of the photon. So Newton would tell us mass of a photon is fixed, speed of a photon is fixed, therefore all photons would come with the same energy. But Planck and Einstein are telling us that the energy of a photon can change depending on its frequency. Now we see that there is a mismatch between what the Newtonian expression for energy is and what the Planck-Einstein expression for energy is, although both of them are using what? The same particle description. So unless we answer this question, then we are not doing a proper job. The word particle would be a meaningless thing, and there is an answer to this. What is the answer to this? The answer lies in relativity. So remember, I told you that Einstein wrote 3 great papers in 1905. It was photoelectric effect, it was Brownian motion, and it was relativity. So it is remarkable that relativity should save us from this problem. But it is not going to save us through a simple expression. It requires an insight. It requires a certain amount of smartness, and let me tell you what it is. So you people have all heard of mass energy equivalence. So what does Einstein tell us? According to relativity, my total energy of a particle is given by m naught c squared over root of 1 minus v squared by c squared. And this is not equal to half m naught v squared. We know that this is not equal to half m naught v squared. So this is my expression for the energy, but still it does not help me, because if I put v equal to c, what will happen to this? If I put v equal to c, denominator becomes 0. This tells me E is equal to infinity. So maybe I was hasty in telling you that Einstein or relativity will save us. It seems to be a contradiction, so we are in for trouble. Newton tells us that all photons should come with the same energy, and this expression for energy is telling us what? All photons have what energy? Infinite energy. We seem to be in trouble, but that is not the way we should approach that. We should do a little bit of more careful analysis. So let us see what we have to do. The way to go around is to look back at the complete Maxwell's equation. So according to Maxwell's equation, my energy density is given by epsilon naught by 2 E squared, and my momentum density. So imagine a plane wave which is coming, and I ask how much momentum is there per unit volume. So I will denote it by pi. This is my momentum density. That is given by u by c. This is dimensionally correct. So both these equation comes from Maxwell. So what Einstein would say, or what we would say with hindsight, is that if you are going to give a particle description for the photon, you should not only be consistent with the energy density description, you should also be consistent with what? The momentum density description. This is my momentum density. After all, in the photoelectric effect, not only did the electron absorb energy, it also absorbed momentum. That is why it is moving at a certain velocity, different velocities, and that momentum transfer is because of this pi. We should be able to write that. So now what I will do, I will write U equal to the number density into h nu, and I will write pi is equal to number density pi is equal to u by c. So what will it tell me? This will tell me that the momentum carried by each photon, so I will denote it by E gamma. E gamma is h nu, and P gamma, momentum carried by each photon, is h nu by c. That is what this relation tells me. So when I try to establish a consistency, this is photoelectric effect, where momentum was not very important for us, but consistency demands that I should associate an energy this. I have to worry about the momentum, and I have to worry about the P. Now, in order to reconcile that, what we have to do is to go back and rewrite the energy momentum relations in a slightly different language. That is the achievement. So let me do that in your next slide. So what is the next slide? I am going to write two expressions. All of you are familiar with this. So my energy density is given by m naught c squared over root of 1 minus v squared over c squared. And momentum, this is the relativistic expression for momentum, is m naught v over root of 1 minus v squared by c squared. So I want to make two observations at this particular point. These expressions are meaningless when I put v equal to c, because I will get energy and momentum divergent. These expressions are trivial if I put m naught equal to 0, because classically there is no particle if there is no mass. Is that right? So put m naught equal to 0 implies E equal to P equal to 0. V equal to C implies E equal to P equal to infinity. Both of them are meaningless. But now I will ask, what happens if I go to m naught going to 0 and V go to C? Now what is happening? The numerator is going to 0, the denominator is going to 0, so probably there is a consistent way of understanding this. That is what we have to look at. So in other words, we are going to look at the limit m naught going to 0, C going to infinity. We ask, are there non-trivial solutions? Just as Maxwell obtained non-trivial solutions in free space, equations were obtained in the presence of what? Currents and charge densities, but the solutions were obtained even in the absence of currents and charge densities. That is how we got the wave solution. We are going to look at that, and the trick is to eliminate V. So let us do that. So I am going to write that again. E gamma is equal to h nu and P gamma equal to h nu by C. This is what Maxwell plus Planck, Einstein are telling us. So that means if I want to get a consistent description of the particle nature of light, I should not only worry about E gamma equal to h nu, we have already accommodated that. We also worry about how to incorporate this expression that the momentum carried by each photon should be h nu by c, because we had two expressions, one for the energy density, another for the momentum density, and there was a natural relation between them. What was the natural relation? We wrote u equal to pi c. This is my energy density. This is my momentum density for a monochromatic plane wave. We have to reconcile these two expressions with the expressions for energy and momentum that come for a particle. That is what we have to do. So in order to do that, I will make a fundamental observation. So we are now looking at particles, relativistic. I need two expressions. The first expression is for the energy, which I will write m naught c squared over root of 1 minus v squared by c squared. And the next expression is for the momentum, when I write m naught v over root of 1 minus v squared by c squared. Momentum is of course a vector, but imagine that it is moving along only one direction. So I have not drawn the vector sign. Otherwise, if you want, I can put a vector sign over that. No big deal. Now there are two important features that we notice. Both of them are problematic, but if we combine both of them, perhaps we can get rid of the situation that we are in. What is the thing? The thing is that if m naught equal to 0, E equal to P equal to 0, which is absurd. That means there is nothing to do. There is no physical system. On the other hand, if V equal to C, we get E equal to P equal to infinity, which is absurd because we don't see any particle with infinite energy. So what are we saying? You can't see a particle with zero energy, it doesn't exist at all, no energy, no momentum. By energy I mean actually the rest energy included. Remember, m naught c squared is there, not just the kinetic energy. So both m equal to 0 and v equal to c are two extreme limits which are meaningless. Now what we want to do is to reconcile the two by taking both of them together and try to get a consistent relation. And the way we do that is to eliminate m naught between E and P and ask if there are non-trivial solutions. So let me repeat that. So E is equal to m naught c squared over 1 minus v squared by c squared. You will use it in your mass defect formula. My P is m naught v over root 1 minus v squared by c squared. So what will I do? I will take the square of E, I will take the square of P, I will get E squared equal to m naught squared c to the power of 4 1 minus v squared by c squared. My P squared will be m naught squared v squared over 1 minus v squared by c squared. A simple calculation will tell you I am not going to work out, and that is you can write E squared equal to m naught squared c squared c to the power of 4 plus p naught squared c squared. It's a very, very simple expression. So you can check that E squared is nothing but p squared c squared plus m naught squared c to the power of 4. So what is happening? Here both E and P were proportional to m. Now the relation between E and P, I should not write P naught, I am very sorry about that. Let me rewrite the expression again. My E squared is equal to P squared c squared plus m naught squared c to the power of 4. So here, if you look at the relation between energy and P, it is not a homogeneous relation. E squared is proportional to P squared, and this is an inhomogeneous term. Inhomogeneous term. And that means if I put m naught equal to 0, there are still non-trivial solutions. So if I put m naught equal to 0, I will get E equal to Pc, which is exactly what Maxwell is saying through the relation between the energy density and the momentum density. So what are we saying? We are saying that there are two kinds of particles. There are particles with rest mass, that is m naught not equal to 0. These particles can never move with the speed of light. If you try to make them move with the speed of light, their energy goes to infinity, therefore they can never move. But on the other hand, there are particles which are all the time moving with the speed of light, but what is their rest mass? Their rest mass is equal to 0. This corresponds to rest mass is equal to 0. Therefore, there is no contradiction. We have put m naught equal to 0 and v equal to c. This equation, however, does not tell us how the energy changes and how the momentum changes. That depends on the physical system. And Maxwell is telling us it changes because of the frequency. That is the input coming from the Maxwell equation. Therefore, we see that it makes perfect sense to speak of the particle nature of light, provided we combine that with the concept of relativity. And we all know that when the speed of a particle becomes larger and larger, when we are looking at higher speeds, we cannot use Newtonian mechanics, but we have to use Einsteinian mechanics, and this is what we have. So this is a very, very important thing for us. Now what I am going to do is to give additional experimental evidence. I cannot discuss it in great detail, but that should restore your faith in the concept of a photon, and let us see what it is. If Einstein is correct, all this should be valid. So first let us look at scattering of light. Light is all the time getting scattered. When the sun's light reaches us, it gets scattered by the atmosphere. In fact, much of it gets reflected from the ionosphere because of the ultraviolet. So in the scattering of light, there is what is called as Rayleigh scattering. Where the initial frequency is equal to the final frequency. The incoming frequency is same as the final frequency. Nothing is going to happen, only the direction of the propagation changes, but the energy does not change or the frequency does not change. But if you believe in the Einstein hypothesis, there is another possibility. What is the possibility? Your radiation was coming inside. Part of the energy can go to the electron, but part of the electron can, a photon can get scattered. That means if I look at the scattered photon or scattered light, I don't just look at the electron. Some of the scattered light must have less frequency than the incoming one. That is what Einstein is saying. Such a phenomena exists. That is the interesting thing. It existed even during the time of Einstein, and that is called Stokes' law. That is called Stokes' law. What does Stokes' law tell you? It tells you that there is a nu here. There is an electron which is coming, and this nu is partially absorbed. I am showing it schematically. So this is my initial energy. This is my final frequency. Nu f is less than nu I, because only part of the energy has been transferred to the electron. Therefore, lambda f greater than lambda I. Stokes had observed this relation, which is not easy to understand from the wave viewpoint of light, but here it is a very natural thing, and Einstein said, you see, there is another experimental evidence for the particle nature of light, namely this is the Stokes' law. This is what is called as a Stokes' law. So we have discussed an additional experimental evidence which we did not think of earlier. That is why I said that Einstein's explanation of photoelectric effect is more robust than the Planck hypothesis. Now if that be true, I should be able to perform an experiment where both momentum and energy can be monitored. And that is called Compton scattering. So imagine there is a photon coming here, there is an electron coming here, and a photon goes out and an electron goes out, gamma, gamma, electron, electron. You can look upon this as a perfectly elastic collision between two particles, where the total energy and the total momentum is conserved. That is called Compton scattering, and I believe quantum scattering was first seen sometime around 1911 or 1912. And if you make use of the full relation E equal to h nu, P equal to h nu by C, you should be able to understand. The last one that we are interested in is what is called as the Raman scattering, and I will leave you people after this. Einstein assumed that in photoelectric effect, only one photon is absorbed. In photoelectric effect. But there is no physical principle which tells us that only one photon should be absorbed. Nobody told me that electron should interact with only one photon at a time. So what should I say? The correct way of formulating this principle is to say that the probability for the interaction between one photon and one electron is much, much larger compared to the probability of an electron interacting with two photons. Or there is also the other possibility that the electron itself gives the energy to the photon in a certain situation. So what happens in the case of Raman effect is actually where the electron gets scattered and actually it can acquire a higher energy. All this time we assumed that my photon is all the time transferring energy to the electron, but electron can also transfer energy to photon. In that case, what should happen? The scattered electron should have a higher frequency. These are called anti-Stokes lines. These are called anti-Stokes lines, and that is the famous Raman effect, which can again be understood as a consequence of the photon hypothesis. So to conclude, what we have done is to give a careful attention to the experimental facts and realize that it cannot be understood in terms of the wave description. But we also said that the wave description has a very robust experimental foundation in terms of interference and diffraction. Then we said, however, interference and diffraction phenomena that we observe involves very large time scales compared to the fundamental time scale of the oscillation, whereas in photoelectric emission very small time scales are allowed. And we said the particle nature is not a very unreasonable thing. That is what Einstein said, and we were able to explain the photoelectric effect. And like any good model, this model exposes itself. It opens up additional avenues to verify that hypothesis, and we showed three particular phenomena. One is the Stokes law, where the scattered radiation can come with a higher wavelength or a lower frequency. It transfers a part of the energy and a part of the momentum. Or Compton scattering, that takes place between a free electron and a free photon, whereas here the electrons are all bound. There you have to worry about the momentum of the electron and the momentum of the photon. That is completely consistent with the particle description. And finally, I also mentioned in the passing Raman effect, where actually the outcoming radiation can have a higher frequency, where the photon is in fact gaining energy. I have not done complete justice to the last part, so don't worry too much about it if you are not following. But the fact is that what Einstein did is not simply a figment of imagination or some kind of a sleight of hand. There is a lot of thought that has gone into it. So if this indeed be the case, that what is classically a wave can exhibit wave-like phenomenon, a natural question arises, maybe what is classically a particle can also exhibit a wave-like phenomenon, and this was the great intuition, great insight of Prince Louis de Broglie, and that we are going to take up from the next class. So now let us stop, have a good time.